So, we have completed the development of all the 32 point groups in 3 dimensions, and in this lecture we will now derive the 3 dimensional Bravais lattices. Once we have done this, then beyond this we will combine the point groups and the Bravais lattices to develop the space groups in 3 dimensions. Now, how do we do this derivation of the 3 dimensional Bravais lattices? Well, it will follow in very similar lines as we had done for the 2 dimensional plane lattices, and in a very similar manner we can do the same thing with the 3 dimensional space lattices. So, what we are going to do is essentially what could be 3 dimensional space lattices? We could take those 2 dimensional lattices in which there are only 2 translations, and now we can add a third dimension to stack those lattices to develop a 3 dimensional lattice. And let us see how this works out. Let us start with an oblique lattice, and if you recall, the oblique lattice is essentially no constraints on the unit cell parameters A and B or the angle between the 2 vectors A and B, and that essentially is what we call as a plane group P1. So, I have this oblique lattice. Now, I want to add a third translation vector C, and I have added this in an arbitrary direction, and this vector makes an angle of alpha with the B axis, the C axis makes an angle of beta with the A axis, and the angle gamma is between the A and B. These are the conventional parameters that we have taken alpha, beta, gamma in this order, and we can now complete the unit cell. So, this is a unit cell in which there are no constraints on A, B and C, because C vector is also arbitrary direction and arbitrary length, and the angles are also have no constraints. So, the resulting 3 dimensional lattice essentially has no symmetry, just like the oblique lattice we started with no symmetry. So, no constraints on unit cell vectors A, B and C, and so essentially that is how one would write this A with a not equal to sign between A, B and C, but this not equal to essentially means no constraints, and no constraints on the angles either. And this, if you go to the list of Bravais lattices, this is what one would call as a primitive triclinic unit cell. So, what did we do? Essentially what we did was we started with the plane group P1, added the third translation leading to the 3 dimensional space group P1, and here we are using the capital letter P to differentiate it with the P1 in the plane group, which uses a small case letter p. So, in all cases, in the 3 dimensional case, we will be using capital letters to designate whether a lattice is primitive or it is body centered or it is end centered or it is face centered. So, this is something that we will maintain in a consistent manner. Now, which point group that the triclinic lattice can accommodate? This is a question. So, one is point group 1. The triclinic lattice is able to accommodate the point group 1, which is essentially no symmetry, but can it accommodate any other symmetry? Well, for now I will just write down that symmetry, and then we will come back to it later, that it can also accommodate the inversion center. In fact, I have pointed this out in an earlier lecture as well, that in all lattices, regardless of what crystal system they belong to, always have an inversion center, only when you add the motif, that inversion center may not be there in the crystal structure. So, any lattice will be able to accommodate the inversion symmetry. So, even if I add inversion, I will still get a primitive triclinic lattice. Now, let us take another example. This time we are taking an oblique lattice with the point group 2, and this is what is the P2 plane group is all about. So, all I have drawn out here the plane group P2 with the two-fold symmetries distributed in the manner with the at the corners and in the centers of the edges and in the center of the cell. Now, I need to add a third translation vector to form the three-dimensional lattice. Now, how do I add this translation vector? Let us try to add it in the way that we had added in the previous case, which was adding a translation vector in an arbitrary direction and of arbitrary length. This dashed line simply indicates that we are in 3 dimensions and these are two-fold axes that will get in the third dimension. Now, I have added an arbitrary third translation C. Now, what would this do? Since I have added this translation will work on all space, this symmetry will work in all space, the translation symmetry, which means that I expect that this two-fold should get translated to a new position. So, now I have another two-fold out here. So, this is a new two-fold that I have got. But then if I look at this now, this two-fold will also work on all space and it will rotate all the other two-folds that are there. In the end, essentially we will be left with no symmetry and therefore, this particular translation is not allowed. So, this brings us to an important principle that when I add a third translation, it must not create any new symmetries, it should preserve the symmetry that we started with. So, this translation is not allowed. So, which translations C are permitted? So, that is the question that we need to answer next, that which of the translations will make sure that no new symmetry elements are created. Let us look at it. Consider a translation C equal to Z, which basically means in the third dimension the Z axis in this case would be perpendicular to the AB plane or basically perpendicular to both A and B. So, I have added a third translation now, it will coincide with the two-fold rotation axis as shown. Now, this will create no new rotation axis and that is one principle that works out here. So, this becomes an allowed translation. Now, if I complete the unit cell, so I get a unit cell like this. And what are the constraints if any? Well, the length on the C vector was not constrained, but the orientation was. So, no constraints on the unit cell vectors A, B and C, but the lengths can be anything. So, again no constraint on the angle gamma because that is how I started with the oblique lattice. However, alpha and beta will have to be necessarily 90 degrees. So, therefore, we will write alpha equals beta equals 90 degrees and no constraint on gamma. And if I go to the list of Bravais lattices, this is clearly a primitive monoclinic lattice. And it is essentially what we call as simple monoclinic and as we know that we use a capital P as a symbol for simple or primitive. Now, are there other C vectors which are possible, which will also preserve the symmetry of the what we started with the oblique lattice? How about considering a vector like A by 2 plus Z? Now, what does that mean? So, you go halfway along A, you reach, so I go, this is A by 2. And then one goes a certain distance Z up. So, the new C vector then simply becomes this, it goes up to some distance Z. Again we see that since this vector ends on a two-fold, this two-fold simply gets translated to the two-fold on the middle of the edge and hence again this gets superimposed. So, hence again no new symmetry axis is being created and therefore, this is an allowed translation. So, what we get is a primitive unit cell, as you can see, with A, B and C, which is also at a certain angle to both A and B. So, the unit cell vectors in this case appear to be arbitrary, but are they arbitrary? Let us consider an alternative. Let us start with the same oblique lattice again, the same C vector. Let us extend this C vector. So, we went to this point and then we came up to here, but now what I can do is I can define a new C vector which would be essentially you go 2C and then you go back minus A. So, to get a C prime vector which is now perpendicular to the AB plane and it is along the two-fold axis. So, C prime equals 2C minus A. So, you go 2C. So, this is the 2C vector and then I go along minus A. So, this is the minus A vector bringing me to C prime. Now, I can complete the unit cell. Now, again I have essentially A not equal to B not equal to C prime and alpha and beta are 90 degrees and gamma has no constraint. Now, how is this different from the previous case? Well, it is different in this manner. When I went from the origin, drew the C vector, I came here, therefore, the lattice point at the origin also gets translated to the lattice point out here. Now, what does this mean? And then once we create a new unit cell, now I have a lattice point in the face center of this cell. So, this is my face center. So, this is the face centered lattice point and obviously clearly when I complete the unit cell, there will be another face center lattice point out here. So, in the end I have a lattice defined by this unit cell where there are lattice points at the corners and there are lattice points on two opposite faces. So, what can I say about it? Again, we have no constraints on the lengths A, B and C prime, no constraint on gamma, but alpha equals beta equals 90 degrees. So, this is again a monoclinic, but it is now no longer a primitive monoclinic, it is a non-primitive monoclinic which we could call it as an end centered monoclinic or a base centered monoclinic. Now, this face where the lattice point is present in the center of the face, this face as you can see is defined as the B face. So, it is on the AC plane, AC prime plane and therefore, it is the B face and that is why you will notice here I have written base centered monoclinic and in brackets B. If it was on the rear face, then this would have been A face and if it is on the C face, it on the top face it will be C centered monoclinic. Now, the thing is one should realize that the base is an oblique plane, it is a parallelogram, while the vertical faces are rectangular faces. So, I will have for the end centered monoclinic, I can have lattice points only on those vertical faces and not on the oblique faces. So, I have basically in this case have two choices to define the end centered monoclinic. Now, I am just trying to explore that is there any other third translation? Well, there can be a third translation starting from again from the origin and moving on and defining it like this as, so this could be C, a new C vector which would be B by 2 plus Z. Well, actually this makes no difference. This will also produce, as you can see, an end centered lattice, but now the face which is centered is the A face. Now, I am looking for some other alternative as well and Here is another possible alternative where the C face, the C vector is defined as A by 2 plus B by 2 plus Z, which essentially means that we move to the, this is A by 2 plus B by 2, and then you move up a certain distance Z to get a vector C, which is something like this. So, it is now ending on the central two-fold axis. So, again this is an allowed translation, no problems. But then instead of defining this, can we do an alternative? So, again I extend the C vector all the way to the two-fold axis on the other corner. So, we have gone up till here, and then I could go, so I have travelled 2C, then I can go minus A and minus B reaching somewhere here. So, this is what I am trying to do, that I have defined a new C vector which is 2C minus A minus B. So, C, A and B, all three are vectors. Again, since the length of magnitude of the C vector can be arbitrary, and therefore, the C prime vector length would also be arbitrary. So, again A, B and C prime are not related to each other. However, the angles alpha and beta, so these angles are 90 degrees, while gamma is unconstrained. So, again this is a definition for a monoclinic crystal, monoclinic lattice with a lattice point, but this time now there is a lattice point in the body centered position, and therefore, this should be called as a body centered monoclinic. However, if I look at the list of Bravais lattices, one will find that the only two lattices that are present in the monoclinic crystal system is simple monoclinic and base centered monoclinic. Hence, so what do I do with this? Well, let us make a little construction. So, we have this body centered monoclinic. Let us take a projection, because I am going to draw a two-dimensional construction that is easier to draw. So, let us take a projection along the z axis, along the vertical axis. So, this is a projection of this body centered cell with the vectors A and B, and the lattice points are also projected, and the central body centered lattice point is also projected on the two-dimensional plane, and this plus half is written to indicate that it is not in the AB plane, but it is halfway up along the C prime axis. Let us draw an adjacent projection of the same unit cell. So, I have now two unit cells adjacent to each other, and let me make a small construction. Essentially what, if I look at this carefully, this is a projected new unit cell in which lattice points are at the corners and there are lattice points at the center of two opposite faces. So, therefore, this is clearly an end centered cell with the B face being centered. Body centered lattice therefore can be represented by an end centered or a base centered lattice. So, therefore, Bravais list does not contain this. However, we will see in the space groups that even body centered lattices of monoclinic crystal system is considered. Now, let us take a different unit cell of the two-dimensional lattices. This time let us consider a rectangular cell and it has a mirror symmetry, which essentially means that we are considering the PM plane group. On this PM plane group, I want to now put a third vector. Now, I am not going to draw a three-dimensional structure for this, rather a projection. So, you can consider this to be a projection with the mirror planes being extended vertically up, and the third projection that I want to consider is C equals VB plus Z. So, V is just a scalar value between 0 and 1. So, we travel up a bit, we travel along B, and then this Z takes me up. So, the projected vector C would look something like this. So, this is a projection of the translation C, but you can imagine that this translation vector is up and it is in the mirror plane. This is important. Since this is in the mirror plane, it also is allowed because it creates no new symmetry. So, no constraints on A, B and C again, because this vector C could be of any length, and A and B to start with were unconstrained. However, you will notice that the angle alpha, so angle alpha, which is the angle between B and C, that has no constraint, but angles gamma and beta are 90 degrees. So, what kind of a unit cell is this? So, this is a basically again a primitive monoclinic unit cell, as you can see, A, B and C no constraint, and two angles are 90 degrees, the third angle is unconstrained. Only difference, if I compare it with the previous monoclinic diagrams that I have drawn, is now the base of the cell is rectangular, while the BC plane is a parallelogram, but the AC plane will also be a rectangle. So, that again two rectangular faces and one oblique or a parallelogram face. Only difference is that now essentially, if you think about it, this is going to lead to a primitive monoclinic cell. Now, same thing we do, or before I go into that, point groups 2, M and also 2 by M can be associated with the monoclinic system. However, it is not possible to associate 2mm. This I will start with the plane group 2mm, add a third translation to figure this out. So, I will leave this as a problem for you to do. 2 by m is also accommodated. This we will see a little later that why 2 by m is getting accommodated. Let us now take a different plane group of the rectangular crystal system. So, this time we are taking a centered rectangular cell. It has a plane group Cm. We have seen this in earlier lectures when we are discussing the plane groups. Again, we consider the translation of the same kind, Vb plus Z. Again, this is an allowed translation, and you can see that A, B and C would be unconstrained, and the angles, two angles are going to be 90 degrees, and a third angle is unconstrained. Therefore, this has to be a monoclinic unit cell, but it is the lattice is end centered monoclinic, because now I have this lattice point at the base of the cell. This way we can continue taking other symmetries, other two-dimensional lattices to create other unit cells of the Bravais lattices. You could consider, for example, plane group P2mm, P2mg, P2gg and C2mm and so on. You can add translations, and these are the allowed translations that I can add to these. Now, I am not going to go through all of these, except that it would be instructive if you go through it yourself, draw such diagrams to show that we can obtain primitive orthorhombic unit cell, end centered orthorhombic unit cell, body centered orthorhombic unit cell and the face centered orthorhombic unit cell. But one should realize that in the orthorhombic case, end centered and body centered are not the same as in the case of monoclinic. Why should that be? You try to reason that out. You can apply a third translation to plane groups P4, P4mm, P4gm and to get primitive tetragonal or a body centered tetragonal. So, that way you will get to the tetragonal crystal system as well. Point groups that could be added to tetragonal lattice we know is 4 and 4mm. So, since we have started with the plane group with the square lattice, so I have the fourfold symmetry present. Now, let us take a very different plane group with the hexagonal, start with the hexagonal two-dimensional lattice with a threefold symmetry. So, that is the plane group P3. We add a third translation, just add it straight up, that will create no new symmetry, and one will simply get A equal to B not equal to C, alpha equal to beta 90 degrees, gamma 120 degrees. This is your gamma here. So, this is 120 degrees and these are 90 degrees. But A equal to B, because that is how we started with the hexagonal 2-dimensional unit cell. So, this unit cell is essentially a primitive hexagonal cell in the 3-dimensional Bravais lattices. These you can get all of this by using other plane groups P3M1, P31M and so on, and you can get the primitive hexagonal unit cell. But now there is another alternative we can do. Starting with P3 plane group, we add a translation 2 by 3A, 1 by 3B plus Z. 2 by 3A, so 2 by 3 along A would take me somewhere here, and 1 by 3B will take me out here. So, we come here, and then you go up along the Z. So, this is how I will get the new vector C, the third translation vector C. Now, let me just change the orientation for this, and let me define this as a C vector, which is the same thing. Now, I can extend this C vector all the way to the other threefold rotational axis. So, essentially I have done C, then extended by another C and another C, therefore, this will have to be a lattice point out here. This will also be a lattice point. So, let me just, so this is a lattice point. This is also a lattice point. From the constraints on A, B, C and alpha, beta, gamma, one can see that this is a hexagonal crystal system, but the unit cell has 3 lattice points per unit cell. So, lattice points from the corners, and then there are 2 unit cells, 2 lattice points inside the cell. This kind of a cell is actually not present in the Bravais lattice, though it is a valid unit cell, but we can do a little reconstruction. Starting with this, we now define alternative axis system A double prime, B double prime and C double prime, starting from this lattice point. So, I define 3 vectors A double prime, B double prime, C double prime. Now, all of these vectors you can clearly see would have the same length. So, all these lengths, so they are constrained in that way that all the 3 are equal, and the angles between them will also be the same. And the unit cell that you get is looking something like this. And if you notice, if I extend this threefold rotation axis, it goes from this vertex to the opposite vertex out here. So, it is basically a body diagonal inside this cell. So, what kind of a cell is this? Well, as I said, the 3 vectors length is A double prime, B double prime, C double prime are equal. The angles are 2 angles are 90 degrees, while the third angle is not 90 degrees, and all the 3 angles are equal, and they are not 90 degrees. So, this is a definition for the primitive rhombohedral lattice, and the constraint is coming from this threefold rotational axis. And of course, we have the rhombohedral axis. So, point groups that may be added to hexagonal and rhombohedral lattices are 3, 3m, 6, 6mm. Now, inversion symmetry has not been considered, though I had made a brief mention of it. So, presence of inversion requires that for every translation T, there will be a translation minus T, and this is true for every space lattice, and hence inversion will impose no restriction on the lattice parameters A, B, C or alpha, beta, gamma. Now, what happens if I add inversion to point group 2? Well, it leads to point group 2 by m. Lattices required by 2 by m would be the same as those required by 2, and if you recall, right in the beginning I had mentioned this, that for a monoclinic system I can have 2, I can have m, I can have 2 by m. And conclusion then is that only a few point group symmetries need to be considered for obtaining the 3D Bravais lattices, and I will just explain to you what I mean here. Laue groups would be sufficient for this. Now, what are Laue groups? We will quickly have a look at this. So, this is the list of Bravais lattices. You see these are all the point groups, this is the complete list. So, all the point groups are mentioned on the right column, and these are Laue groups. So, you will find that only some of the point groups have been taken out from here. For example, only 4 by m is considered, and this particular 4 by m are considered. Similarly, in this only one point group is considered. Like that you will find several things. For example, here this is considered, and in this triclinic, out of 1 and 1 bar, only 1 bar is considered. What is common in all of these so called Laue groups? What is common is that they all have inversion symmetry. So, one could only consider the Laue groups, and that would be sufficient to derive the Bravais lattices. But one thing to note, we have only derived 11, the 3 cubic ones have not shown up. Well, for cubic lattices, we can just consider these point groups 2, 3 and 4, 3, 2, and how we can get the cubic lattices is you could consider, for example, tetragonal lattice. If I take a tetragonal lattice, so if I consider a primitive tetragonal, so what it has a 4-fold rotational symmetry. Now, if I impose 3-fold rotational symmetries, if I impose one 3-fold rotational symmetry along a body diagonal, this 4-fold will take it to the rest of the body diagonal. So, we will end up getting 4 3-fold rotational symmetries, and this will lead us to basically simple cubic. Simple cubic unit cell. Similarly, if you take body centered tetragonal, you will get a result of body centered cubic. If I take basically an end centered tetragonal, I will end up getting a face centered cubic. So, all the 3 unit cells can come out of tetragonal. Similar thing I can do with orthorhombic unit cell, which has only the 2-fold rotational symmetries. I will get the same 3 cubic cells, making a total of 14 Bravais lattices. Now, in the final conclusion, there are some conventions for the parameters of the unit cell. So, first one is select the shortest translations in the lattice A, B and C. So, we do not need to consider big unit cells, but there may be further constraints there of symmetry. Now, if there is nothing special about any axis, now what does that mean? Well, for example, if I take the orthorhombic unit cell, it has along A, along B, along C are all 2-fold rotational symmetries. They are all the same. So, there is nothing special about any particular axis. Triclinic again, there is no symmetry along any of the axes. So, again there is nothing special. In that case, we use this convention that A greater than C and B will be greater than both A and C as well. So, this is a convention that is used. Now, C is generally defined as a unique direction, but that may not necessarily be true in all cases. So, C generally defined as a unique direction means there is something special about C. In the case of the tetragonal cell, 4-fold axis, so is a unique direction, and a general convention is that one can put the 4-fold rotational symmetry along the C direction. In the case of monoclinic cell, it will be the 2-fold axis that is going to be the unique axis, or if it is just a mirror on the base of the cell, then the mirror will be perpendicular to the C axis, and hence the C axis is the unique direction. In the hexagonal cell, it will be the 3 or 6-fold axis. Now, I conclude this lecture here, and in the next lecture, we will start developing the 3-dimensional space groups.